Hello, it's our Tuesday morning video. So today we are going to look at one of those volumes of revolution that we started yesterday, and I'm just going to show you how to do one when it goes around the y-axis and give you a couple to do. Then when I get in, we'll check it on the homework, see how that went from last night when we were going around the x-axis. Alright, here is the problem I need to show you. Find the area bounded by these lines. So let's get a sketch going. I'll sketch it over here where you can't see while you're sketching it fairly large. Alright, I'll show you my sketch. Here's the graph, the smiler, y equals x squared. The horizontal line, y equals 2, and the y-axis form the boundary lines of this area right here. And I'm going to revolve that around the y-axis this time. So it will actually create the same boundary that's already there from our function y equals x squared. So this is a round solid bowl, and I am going to indicate one sliver of it. So I'm going to cut it right here and form a cross section. It's like I'm taking a saw and I'm cutting right through it. And we talked yesterday that the cross section that is created, if I was going to lift it up and look down at it, it would be completely circular. So hopefully that makes sense to you. So every circle has a radius, so I'm going to draw that radius in. That radius I'm going to hook to my function and call the point where the radius touches my function xy. That sometimes helps. Alright, so we learned yesterday that the area of a circle is pi r squared. So the area, this becomes a volume now because it actually has a slight thickness. But that thickness is just a very thin, infinitesimally thick or thin thickness. So it still is a thickness, but it's very, very small. In fact, if I was going to put my thumbs on that thickness, they would show up right there. And I can read the distance between my two thumbs on the y-axis. So it's a very small change in y. So that change in y is going to show up in my problem as a dy behind the integral. So the area is pi r squared, and the thickness, the height you might call it, of this tiny skinny cylinder, this thickness right here, which is shown up on my picture right there, is a change in y so small that we call it dy. Alright, so the radius I pictured right here, and that is, if I went over x and up y to get to this point, you'll notice that this radius is simply a mimic of this x value. So I can replace the r with an x squared. However, the boss here says I have to do this problem in terms of y. So I look at my function and see if I can just put it in view here. Y equals x squared. So I see that this can be substituted for y, because y and x squared is equal. So I put in behind my integral, wait a minute here, y equals the quantity x squared. Right, so I just put in y and dy. And the only thing I have to do now is come up with my limits of integration. And that corresponds to, up in my picture, this little circular sliver, we call it a disk. They're going to stack up on top of one another in this pile. And it's going to go from the bottom of this figure to the top. And that represents the limits of integration. Where will this stack begin and where will it end? So in this picture, it's going to go from 0 to y equals 2. So 0 to 2. And then we're ready to complete the problem. Integrating, we get pi on the outside, y squared over 2. Evaluate it from 0 to 2, becomes pi times 2 squared over 2, which is just 2 pi. So those are volume units, so we can say units cubed, if we want to be technically correct there. All right, so you see how the picture and the equation works very similar to what you saw yesterday. So that example should get you through classwork for today. So we are going to do on that same page that I handed out to you, I think that was page 465 that I copied, and I want you to do, it was 7.2 as a section. And I want you to do numbers 7, 8, 9, and 10. 7 through 10 as your classwork. And I'll be in to check those in a little bit. So, over and out.